So over the past few days, we've been graphing with Trig, and today we're going to kind of bring together that with some more real-world application and talk about how do we actually create models that describe these real-world scenarios. So the first thing that we should note is that most of the time when we are dealing with anything that continues in a cycle or like cyclic data, so examples of that are heart rates. Examples of that are anything that moves in a circle and continues, gears, all those types of things, waves. They continue to move within certain boundaries for large periods of time. So our very first example we have here is with a Ferris wheel. The height of a person in a Ferris wheel, on a Ferris wheel, is given in the table below. The distance d of t in meters above the ground is a function over a period of time in t seconds. Data is shown in the table below. So let's talk about a few things we know about Ferris wheels. We know that you get in on a Ferris wheel and you go around in a circle, right? And you continue to go round and round and round and round on the Ferris wheel. So what's going to happen is the height of this person is represented at 0, we're 30 meters high, then we're 50, 30, 10, 30, 50, 30, 10, 30. And what we should notice is that this is going to be repeating through these values over and over. So explain why a periodic function is a good model for this data set. You can say anything about how the values are going to repeat. So those same values, the same y values will continue to repeat. What is the amplitude of this function and what does it represent in terms of the situation? Let's actually start to graph that. You could probably figure that out just by looking at what's going on here, but it looks like my highest value is 50, my lowest value is 10. I'm counting by 60, so here's going to be 60, 120, 180, 240, 300, and I just kind of skipped ahead and got my values done here. So there's 10 to 60. Now, I know that we're starting off, I'm just going to get some of these points graphed. So we're starting off at 0, 30, 60 goes up to 50, 10, 20, 30, 40, 50. Go ahead and plot all of these points here. All right, so once I check this out, it looks like this 30 is going to be my midline. Usually your midline is the point that's going to be repeating through your cycle the most, right? Because it has to pass through, or your graph has to pass through that midline multiple times to get to the highest and the lowest point. So it says, what is the amplitude of this function and what does it represent? Remember, the amplitude is the total distance divided by 2. So if our total distance, the absolute value of the total, is going to be, we're going from 10 to 50. So our total distance is 40 divided by 2 is 20. And that means that from the starting position, you are going to go 20 meters above and 20 meters below that starting position. All right, so something about 20 meters above and below that's midline or that starting position of 30. What is the period of the function and what does it represent in terms of the situation? So the period is how long does it take to complete one cycle. So I can look at my table here and I see that it starts repeating its values at 240. I can also look at my graph and see that I cycle through all my values here from 0 to 240. So the period is going to be 240 seconds. And we should say something about that's how long it takes for us to go one full rotation in the Ferris wheel, right? Because we're going up the wheel, so we're going up, we're going down, up. So it takes 240 seconds to do one full rotation. Part D says give a trig function that models this data where f of x is the distance in meters and x is the time in seconds. So now is when we're going to actually start writing this function. We have to choose between sine and cosine. So if I'm thinking about my sine and cosine graphs, I know that my sine curves look like this. My cosine looks something like that. So if I'm thinking about which one of these is going to be easiest to manipulate, Technically, since my cosine curves keep on going, right? Technically, cosine and sine cover the exact same values, but we're going to have to do less work if we choose to work with a sine curve. So a sine curve starts at that midline or that baseline, and then it moves through. So let's just call this a sine function. We're going to go with the sine for now. So I'm going to say f of x equals something sine of something x plus or minus something. We know here that, let's see, we're not going to do any left or right shifts, but we shifted up to have a baseline of 30. So I'm going to come here and I'm going to say, all right, I know that since my baseline is 30, I'm going to say this is plus 30. I also know that I solved for my amplitude earlier, and my amplitude was 20, so this guy's going to be a 20. Now, my period is 240 seconds, but remember that I can't just plug in 240. The value that gets plugged in here needs to be solved for to get 240. So we know that we solve for period by saying 2 pi divided by whatever that value is, and that needs to equal 240. So we're just going to solve for what did I divide 2 pi by in order to get 240. Let's put this 240 over 1 and cross multiply. It's going to be the easiest for me. So I get 240b equals 2 pi. And when I simplify that, I get pi equals, or b equals pi over 120. So what that coefficient is going to be pi divided by, and let me get this a little bit cleaner. $120. And again, remembering that this value right here, this b value, you cannot just say, oh, 240, done. You need to use the formula that 2 pi divided by b equals our period. Key takeaway there. Let's go over one more real-world example. Bella used a motion detector to measure the horizontal distance between her and her younger sister on a swing. She stood in front of her sister and recorded the distance in meters over a period of time t seconds. The data she collected is given in the following tables. So I want for you guys to take a second and answer part A. It's going to be very similar to what we just did. And then after you get that done, let's make ourselves a graph. So answer part A, and then I want for you to give me an x and y axis, where this right here is going to be time in seconds, and our y-axis is going to be distance in meters. All right. I said something about our y values will continue to cycle through the same values. Remember, your answer does not have to look exactly like mine as long as it's saying something about repeated outputs. The other thing was that when we're setting up our graphs, make sure that you're using an appropriate scale. So I looked at this graph and I noticed that there's a bunch of decimal points. It is not reasonable for me to try to meet the needs of every single one of these, but I do notice that my x values are moving at 0.2 pretty consistently. So I made my x-axis move at 0.2, so 0.2, 0.4, 0.6, 0.8, 1, 1.2. And then my y values, I just knew that I had to get very close to 4 and then go down to about 0.6. So I made them move by 0.5. And actually, let me add one more little tick mark here and make that 4. What I want for you guys to do is take a second and plot all these points on your graph. And then answer question B about the amplitude, question C about the period, and then start to try to work on D. Okay, let's go over that graph really quickly here. So again, let's make sure we're doing it as curved as possible. Obviously, this is real world data, so it's not going to be super accurate, but I can make some assumptions here. It looks like 2.2 is the value that we keep on coming back to. So I'm going to say that our midline is probably going to be about 2.2. I also know that my lowest value I go from the midline is 0.6. My highest value is 3.8. So that gives us a total distance of 1.6 above and below the midline, which means that my amplitude is going to be 1.6, and that 1.6 represents how far Bella's sister is traveling to and from Bella. So Bella seems to be standing 2.2 miles away from that motion sensor, and she's going 1.6 meters. If you think about a swing set, right? Here's a swing right here. That swing is going to be swinging here. It's going to be going 1.6 meters to and from Bella. There's my beautiful drawing. Here's Bella right here. And here's her sister, and just pretend she's in the swing. 1.6 meters this way, 1.6 meters this way. What is the period of this function, and what does it represent in terms of the situation? So when I see how long does it take for my values to start repeating themselves, it takes all the way 1.246. And if I look right here, let's just verify. Yep, at 1.6 I get all the way back through one cycle. So I'm going to say that 1.6 seconds is the period. And what it represents in terms of the situation is that that's the amount of time it takes her sister to swing to and from Bella. Now, when we're writing a trig function for this guy here, remember we always want to take the path of least resistance. So here's my sine curve. Here's my cosine curve. And we didn't talk about this explicitly, but if you think about both of these models moving continuously, sine, cosine, we should notice that they both look very similar to each other, and you can actually change a sine curve into a cosine curve by just having a horizontal shift. So we could just move this over here, right, and then it's a sine curve, or we could take this cosine curve and move it just a tiny bit left to make it or the sine curve and make it into a cosine curve. But I always want to do kind of like the least, right? I'm always looking for like, what is my path of least resistance? So if I have a curve that doesn't need any transformation to look exactly like my data, that's just what I'm going to use. A cosine curve I know starts high without any sort of a phase shift, so I'm just going to use a cosine curve here. And I'm going to write my blank template. So I'm going to say f of x equals, and I'm just going to start filling things in. We know where my midline is. My midline is what value do I continually come back to pass through, and that midline in this situation was 2.2. So I'm going to say that this is going to be a plus 2.2. I also know that my amplitude is going to be 1.6. So I'm going to plug that 1.6 in for my amplitude, because from 2.2 we're going 1.6 above and 1.6 below. Now I know that my period is also 1.6, but remember we can't just plug in 1.6. This value, this b value that exists as the coefficient of x, is 2 pi divided by something, and that needs to equal 1.6. So I need to know what is that something that when I plug it into the denominator of 2 pi, it generates an output of 1.6. We can do a few things here. We can leave 1.6 and do that over 1 and cross multiply. I can also change 1.6 into 16 divided by 10, and I think I'm actually going to do that here, because that way I don't have to work with any kind of decimals. So I'm going to say 20 pi equals 16b divided by 16. And let's actually simplify this a little bit more so we can get it as clean as possible. These are both even, so I'm going to take that down to 10 pi divided by 8, and I can take that down some more. So I'm going to also simplify that down to 5 pi over 4. And that is going to be my x coefficient. Now, once again, we have pi, and let's address this really quickly, because in the past, we did not see a pi value in front of my x or my coefficient of my x. If I do look at my count, I don't notice pi in any of my count, and on the examples that we did yesterday, they all had pi in their count. So if I'm doing this, and let's just kind of show this check, if I come over here and I say, what is 2 pi divided by 5 pi over 4? What that looks like is 2 pi divided by 5 pi over 4, so we have 2 pi times 4 over 5 pi. And much like when we convert from degrees to radians, we like that pi in that answer because it cancels out. And then I'm left with 8 over 5, which simplifies down to be 1.6, which is exactly what we want. So it's okay to have a pi in that answer, and we want that because our count on our x-axis and on our x values is not in terms of pi. What I want for you guys to do is work on some of those examples. There are going to be videos attached if you are struggling with them, and we are going to continue this modeling through next week, but we're going to be using some real-world scenarios and data collections, which is super exciting. So I will see you guys then.